This is Chapter 4, goal number 23, and with this lesson we will complete our study of inverse trig functions. We're still evaluating composite trig functions. However, you'll notice that in this case we are evaluating sine of inverse cosine, cosine of inverse tangent, sine of arctangent. In other words, we are not evaluating functions that are inverses of one another, but we are mixing functions together. So in this case, our shortcuts will not apply. Sine of an inverse cosine will not use cancellation rules like sine of inverse sine. So let's discuss example A. We want to find the exact value of sine of the inverse cosine of 5/13. So I still analyze this to see that inverse cosine is on the inside, therefore I will find theta on the inside, and then I will evaluate the sine of angle theta. So my final answer will be sine of some angle theta equal to opposite over hypotenuse. So initially I'm finding an angle, and then I will evaluate the sine of that angle. 5/13 is definitely not a value that we have memorized on the unit circle or in 30, 60, 90 or 45, 45, 90 right triangles. So when our inverse contains a value that we have not memorized, we'll have to draw a triangle. Inverse cosine, we have learned, lies between 0 and pi. In quadrant 1, inverse cosine is positive, and in quadrant 2, it is negative. So we will sketch the corresponding triangle for 5/13 in quadrant 1, where cosine is positive. Remember, our angle theta is always with the x-axis to rely on the concepts and properties of reference angles. And then the numerator is 5, so the adjacent leg is 5, and the hypotenuse is 13. So remember, we are evaluating the sine of angle theta. We use the cosine to find theta, but then we'll evaluate the sine of that same angle. So because we have a triangle, it's not necessary to know the value of angle theta. It's just necessary to know the sides of the triangle. I want you to take a moment and find the missing side of this right triangle. You may have recognized that this is one of the triangles in our family of Pythagorean triples, 5, 12, 13, and if you didn't, you can always apply the Pythagorean theorem to solve for the missing side. So now that we've set up our triangle, we can now find the sine of angle theta, which is 12/13, or opposite over hypotenuse. Let's look at example B. Find the exact value for cosine for inverse tan of 2√3/3. Again, the inverse is on the inside, so that means I will be finding an angle measure on the inside and then follow that by evaluating the cosine of that angle. And remember, cosine is adjacent over hypotenuse. So 2√3/3 is not part of one of our special angles, so again, we will have to draw a triangle in order to find the cosine of angle theta. Inverse tangent, we know, is restricted to -pi/2 to pi/2. 2√3/3 is a positive value, so we will draw our triangle in quadrant 1 again. Recall, tangent is opposite over adjacent. And in order to find the cosine of angle theta, we will need the hypotenuse. So we will use the Pythagorean theorem. So c squared equals a squared plus b squared. 3 squared is 9. And as a reminder, 2√3 squared, we're multiplying 2√3 times itself So we'll need to multiply 2 times 2 is 4. Root 3 times root 3 is 3. And then if you struggle with what should we do with the 4 and the 3, make sure you notice that this is 2 times root 3 times 2 times root 3. So because each of these factors are being multiplied, we simply multiply 4 times 3. So 9 plus 12 is 21. And remember, that's the value of c squared. We have not yet found the value of c. And so to do that, we simply take the square root of both sides. The square root of 21 will not reduce, so we will leave that as the square root of 21. So now that we have our triangle, we're now ready to evaluate the cosine of angle theta, which is 3 divided by the square root of 21. If you'd like to rationalize, you may. We would multiply numerator and denominator by the square root of 21. And that gives us 3 root 21 over 21, which will reduce to it will not reduce to 3 root 21. It will reduce to square root of 21 over 7. In example C, we're asked to find the exact value of sine of arctan of x. This might seem a little odd to you that we would be evaluating a trig function which contains a variable. We will do this the exact same way as if we had constants with which to evaluate. So I see that we have arctangent on the inside, which means I will need to set up a triangle to find the values for theta. I know that tangent is opposite over adjacent, so I'll make x a fraction by putting x over 1, and now I'll draw a right triangle. You can always assume that the variables are positive unless you are told otherwise. So our triangle would be drawn in quadrant 1. Opposite side is x, adjacent side is 1, and because we are evaluating the sine of angle theta, we will need to find the value of the hypotenuse. So as usual, we will use the Pythagorean theorem, a squared plus b squared equals c squared. So c squared is equivalent to x squared plus 1, and then to solve for c, we simply take the square root of both sides. X squared plus 1 is not a perfect square binomial, so we cannot take the square root of that. It's prime, so our hypotenuse is the square root of x squared plus 1. Now that we have found all the sides of the triangle, all the sides that correspond to theta, we can now evaluate the sine of angle theta. And the sine of angle theta is the opposite x over the hypotenuse, the square root of x squared plus 1. I will not require you to rationalize this, so you can leave that function as is.